We've talked about insertion at length. Now let's talk about deletion to make the picture complete. Welcome back to this discussion of the maintenance of B+Trees. Let's now spend this video, only this one video, on deletion. And what you will see is that some of the ideas, the basic ideas of the insertion into B+Trees are mirrored here in a sense. So there's a quite nice correspondence between the techniques and how you react to particular situations like underflow and overflow. These are in some sense counterparts to each other, and I think that's it completes the picture in a sense and makes this a homogeneous complete thing. Okay, so let's see how B+Tree deletion is going on. All right, so in this case, what we will find ourselves in is a situation in where, let me increase the pointer size here, all right, is that we are passing a key, just a key to the B+Tree deletion algorithm. We don't know about the rid, of course, of the row that we want to delete. This is just the thing that we are going to find in the B+Tree and then remove from it. So all we know is that the entry with key K has to go. All right, so that would be the only input that we receive for B+Tree deletion. Okay, so what we then would do is, of course, use our search routine. Again, find the search routine to find the leaf node P that should hold the entry with the key value K. Okay, so we'll probably find that entry there. If we do not find that entry there, well, then it has not been stored in the B+Tree at all, and our deletion is done already. Stuff that has not been stored in the B+Tree cannot be deleted. So, story over. Otherwise, we simply delete this key value and its associated RID from leaf page P. And now let's check the state of leaf P after we have deleted this one entry. If the leaf now holds less than order entry, less than O entries, we have to react, because now our leaf underflows and violates our minimum occupancy rules. At least O entries, order entries, have to be stored in one such node. Okay, so it's not acceptable to underflow. We have to react here. Okay, so and how deletion routines normally would react is to look at the sibling nodes. Look at the sibling nodes of this leaf node P. If there is a sibling node that has some entries to spare, that is actually very well packed and could spare one entry, then we would redistribute this particular entry and move it over from that sibling node into the underflowing node P. All right. So then the node P would have its original occupancy again, its occupancy of O now, and well, the sibling node of P has now one entry less, but that's fine because this was a node that had something to spare. If there is no such sibling, that has something to spare, that means that the siblings or the one sibling of our leaf node P has only O entries. So also the siblings are really very weakly packed at minimum occupancy. Then we can perform merging. So the leaf node P only has O-1 entries. That's why we are in this situation that we have to react to the underflow. So O-1 entries. One of our siblings has only O entries, otherwise it would have something to spare and we could use redistribution. Okay, so P prime should be our sibling leaf, okay, and it has only O entries. So we can now merge P and P prime to form a single leaf node. All right, so the entries of P and P prime are now forming a single leaf node of 2 O-1 entries. All right. In future searches, we don't have to discern between descent into the leaf node P or the leaf node P prime. All right. So the separator that formerly discerned the two leaf nodes is not needed anymore in the common parent of P and P prime. That separator can be deleted from the inner node. And this, of course, leads to recursive deletion in the inner node. And just like insertions, deletions can propagate upwards the tree. Okay. Such deletions may propagate upwards the tree even up to the root node. And the deletion of a separator may leave a root node empty. Recall that there is no minimum occupancy for the root node. The root node may only hold a single entry. We have seen it before in our examples. Deleting that one entry from the root node will leave the root node empty. It can be garbage collected and removed, and we can establish a new root node. The just merged inner node can be made the new root node, and the height of the B+Tree has decreased. The path length from the root to all other nodes in the B+Tree has decreased by 1, and all the things remain balanced. Okay, so this would be the case that the height of the B+Tree indeed shrinks. Let's look at a few examples here. Okay, so let me switch on the light again, make it more focus. Right. So let's see. This is the given B+Tree situation. You see that's a single root node and 2 immediate leaf nodes. Under this very small, but it serves for our examples. So delete entry with key equals 19. All right, we would perform a search starting at the root node for the key 19, and that search would lead us to this leaf node 1 here. There is indeed an entry with 19, so there is really stuff to be done. Removing 19 from this leaf node 1 will leave us with the occupancy of 2 entries. The order of the sample B+Trees here on the slide is 2. The fanout or the maximum occupancy is 4, but so 2-0, but the order is 2. 2 entries is still acceptable. So just remove the 19 from this leaf page 1, leaving us with 2 entries only. So that would be the new situation. Everything else stays the same. Deletion over already. That's the really simple, easy case. Okay, more deletions on that tree. Let's delete an entry with key equals 20. Okay, search again, starting at the root node, being led to this page, the leaf page 1. And we indeed find an entry 20 here. Something has to be removed. We will remove the 20. This leads to an occupancy of only 1 entry, which is below the minimum occupancy rules of 50% or order 2. All right, so this is not acceptable. The first thing that we will look for now is a sibling leaf. There's only one sibling here, page 2. A sibling leaf that has stuff to spare. We can indeed spare 1 entry here in this sibling leaf. Removing that entry and moving it over to leaf node 1 would still leave us with 2 entries here, which does not violate the minimum occupancy rule. So indeed, redistribution, leaf node redistribution is indeed a viable option here. Okay, so the 20 is gone. The 24 is being moved over. So that would be the new occupancy situation in the leaf node 1. 24 has gone from here. Okay. To repair the tree search property, we need to place or replace the former separator 24 between these 2 leaf nodes by the new separator 27. And indeed, it's now found here in the inner node. So the inner node has undergone a replacement of separators, no further deletion or something in the inner node, everything remains stable otherwise, and we are done with our deletion in this particular case. More deletions. Now let's delete the entry with key equals 24. Okay, so I think that things are getting really thin now here. So let's see. We are looking for the 24 starting at the root, being led to this node, the leaf node. Indeed, the 24 is to be found. Something has to be removed. Okay, so let's look. Let's look for a sibling that has something to spare. There's only one sibling node regarding this situation. It's this node, and there is nothing to spare. We are already at minimum occupancy in this leaf node 2. Okay. So now what we will do is leaf node merging, all right? So removing the 24 here leaves us with 1 entry. 2 entries are being moved over from this leaf node 2. This leaves us with 3 entries or 2 O minus 1 entries. here are the 3 entries that are now located in the single leaf node 1. Leaf node 2 actually serves no purpose anymore, so we mark it for garbage collection. So depending on the implementation of the reclaiming of heap file pages in our database system, this page will be removed from the heap file, from the B+Tree heap file, and will be gone in a short while. It's been marked as being obsolete here. Okay, the former separator 27 that was discerning between the leaf node pages 1 and 2 is obsolete now. It can be removed recursively from the parent node, and as you can see, indeed the 22 entry has gone together with its page pointer, of course. So what we have removed is indeed the 27 along with its page pointer. Wait, let me make this more focused. So we have really moved this entry, the key entry along with its page pointer is gone now, and we are left with such a root node here, a root node that only occupies a single, that's only occupied by a single entry here. Okay, so this entry served the purpose of leading us either into this node here or into this node that's behind this symbol, subtree symbol 3. Okay. So in the meanwhile, let's assume that somebody has already also removed the 27 here. So even that is gone by now. Okay. So the 27, removing the 27 is no problem because leaf node 1 has something to give here. The 27 can go without violating the minimum occupancy. Let's assume the 27 is gone already. All right, so now we've unfolded the subtree 3 that I was just mentioning. So it's now really made visible here because things are so sparse already in this B+Tree that we have to look at all of it. So there's not much left here in the B+Tree. Let's delete further stuff with key equals 35. Okay, so again, search the tree starting from the root node. Okay, and that leads us into this rightmost leaf. Deleting 35 is indeed something that has to be done. There is a 35, so let's remove it. Okay. There's an underflow in this page now, and we would try to use redistribution from our sibling 1, but that's no option. Minimum occupancy here over here at leaf node 1. So what we will do is merging of these entries. So this entry and this entry, the 35 is gone, the 33 is still there. These 3 guys, they make up the values inside the leaf page 1 now. All right, we don't need the separator between the page 3 and the page 1 anymore. It can be removed. So this guy can be removed along with its page pointer. All right. Okay, if we do that, then this leaves the old root node 0 empty as well. As you can see, there is nothing more in here. So this leaves the page 3 empty, and it has been marked for reclaim, and it leaves the old root node empty, and it has been marked for garbage collection as well. All right, this is the case where indeed the new root node, a new root node has been established inside this B+Tree. This is the new root node. The B+Tree height has indeed decreased by 1, and everything remains balanced as well. All right, so this is the rare case, of course, where the B+Tree indeed shrinks. Okay, so this closes the discussion of deletion actually already. We have discussed leaf node redistribution, and we've discussed leaf node merging. And for most of the implementations, the story would end here. Okay, the story would end here. There is no special treatment for the deletion and the underflow of inner nodes implemented in most commercial and also in the PostgreSQL DB B+Tree implementation. Of course, redistribution and merging could also be applied to inner nodes, and that's what's shown on the next 2 or so slides. But just as a comment, this is sometimes not found in actual B+Tree implementations because of the complexity involved and the diminishing returns it promises. But it's still possible to implement, so let's have a quick look at that. So redistribution could also be performed for inner nodes, okay? We have only applied it to leaf nodes for now, but we could apply it to inner nodes. So assume situations like this, probably some deletions have happened in this part of the tree, in this right hand side part of the tree. And recursive deletions and the removal of separators have led to a situation in which, in which this inner node has gone down with its occupancy to a single entry. This is already below minimum occupancy rule. This is not acceptable there because this is an inner node that's not a root node. Okay, so inner nodes should be filled with at least order, so 2 in this particular case, entries. So what we could try now is redistribution, because there's a sibling inner node here that has some entries to spare. At least it even has 2 entries to spare. So what we'll do now is what's being indicated in this paragraph here. We will rotate this rightmost entry here. We will rotate this rightmost entry through the parent and place it over here. The 30 is shifted over. This is the situation that you find here. So we move the 20 and place it up here in the parent. This 20 kicked the 22 downwards into the rightmost inner node here with number 7, and it's being placed there now, shifting the 30 over. Okay, so this is what I meant by rotating through. So we are rotating the entry, we place its separator entry here, and its page pointer is being moved down here. You see the rightmost, the page pointer of 20 has been pointing to 6 here, and you will find that subtree 6 now wired in at this place. Okay, so this is one of the more complicated rotations and manipulations that you can do a B+Tree structure. And maybe that's also the case why you don't find it implemented in practical systems. But let's see that everything is okay. And regarding the search tree properties of this tree, nothing has been destroyed. So in this original situation, let's look at the semantics of subtree 6 of this subtree. Okay, so looking at the separator values, which values do we expect to find in the subtree 6? Okay. These are the values that are less than 22 and they are larger or equal than 20. Okay, less than 22 or larger or equal than 20. Okay, after all this manipulation stuff, what do we find here? Subtree 6 is located down here. So to get there, we have to search for values that are larger than 20, larger or equal than 220, and less than 22. This is exactly the situation that we had before on the left-hand side of this diagram. So this is actually the situation here. This is the condition that characterizes the entries in subtree 6 before and after this tree manipulation. Everything is under control. Okay, and we are left with 2 inner nodes that fulfill the minimum occupancy rule, no further propagation of deletion upwards the tree. Okay, so that would be inner node redistribution. If the situation is even more dire and even more entries are missing from the nodes that we are manipulating here, then the situation may look like this. Again, let's assume that some deletion has happened below this inner node 5 here in the right hand side of the tree. Okay, so we have pulled and removed some separator and its page pointer from this inner node 5, and indeed it has underflowed as indicated by this lightning symbol. So let's look for help, and let's look for sibling nodes, sibling inner nodes that could spare some entries. There is only one sibling, it's this page 1. There is nothing to spare there. Already minimum occupancy in this inner node 1. What we will do now is to merge two inner nodes, What we find here, the load that we find here, is being moved over to this sibling node 1. All right. This leaves this inner node 5 completely empty, and indeed we will mark it for garbage collection once all of this manipulation has been performed. Okay, right. The 30 has been moved over. This means that the separator between the two, the separator between the nodes 1 and 5 is not needed anymore, and it can be deleted from the node above. But as you can see, it has been pulled down and placed here to discern between the subtrees 4 and 6. Subtrees 4 and 6 in the new situation are part of the same inner node now. We need a separator that discerns the entries between the subtrees 4 and 6. And it's exactly the separator 22 that can perform its job. You see that it has been removed here and has been pulled down. So deleted recursively and being pulled down into this inner node 1. Of course, this also means that we have to perform deletion recursively in upwards the tree here. This is the root, so everything is fine. But otherwise, deletion would have to be propagated upwards the tree because we've removed the separator 22. Again, let's check that the search tree properties have been preserved. So let's see. How about the semantics of the entries in subtree 4? Okay, so before all of this manipulation, in subtree 4 we found entries that are less than 22 but are larger or equal to 13. Okay, less than 22, larger or equal to 13. How about the right hand side here? Okay, so less than 42, okay, but that's fine. But well, here we are talking about this tree. Okay, so the entries here are less than 22, okay, but they are larger or equal to 13, which is exactly the situation that we found before, and it's indicated here. The other thing that has moved is the subtree 6 here. Let's look at the subtree 6. You can ask yourself whether everything is okay for subtree 7, but let's look for subtree 6 here. Subtree 6. So the entries in subtree 6 are larger or equal to 22, but less than 30. Okay. Okay, less than 42, that's fine. It has been the case before. Okay, so the entries in subtree 6 are larger or equal to 22 or less than 30. Okay, so pulling down the separator 22 into this new inner node 1 here has done its job correctly. All right. It's exactly the separator that we needed to discern between the two subtrees. Okay, so everything has been referred, everything is fine. This is B+Tree deletion with inner node redistribution and inner node merging. As I told you, the last two steps, the operations on the last two slides, are not often found in B+Tree implementations because they are somewhat complicated. And well, practice has shown that the win that you get there is minimal. All right, so why bother with the complication if you can do without? Actually, the B+Tree implementations in real commercial systems, IBM DB2, for example, have been stable and are being left alone for many releases of the database system. You can imagine that the B+Tree implementation are really at the heart of these systems. Fiddling with these implementations, optimizing their behavior and so on, is something that should be considered very carefully. Breaking behavior inside this very core of the query engine of the database system would be fatal, of course. So B+Tree implementations tend to be very stable and rather old, actually, in most systems. All right. Okay. So that's about it. That's about the maintenance of B+Tree entries. And this is one line that we can draw again in this B+Tree chapter. There is a bit more to say about the internal nodes and the inner nodes and how we can optimize their layout, and we will talk about this in the next video. But we are nearing the end of our discussion of B+Trees. There is something to be said about ordered indexes in MongoDB, although the story really is way different there. Okay, I hope you will be around when we read this part of the course. I'm surely looking forward to that, and hope to see you there. Bye.